Chapter 9, Section 2, we look at the second condition needed to achieve equilibrium. Imagine a situation where you're going to a party, you have this fancy new costume you want to show off. So when you arrive at the door, you want to make a dramatic entrance. So you throw open the door to show off your costume. And we know from everyday experience how doors operate. So let's take a look at figure 9.7 here. This shows different situations of opening a door. In part A, we have a force applied to the door. The hinge is over here on the left. The force is applied near the handle, a certain distance away, and we're pushing perpendicular to the door. So with a large force far away from the hinge, the door opens quickly. In a similar way, part D shows the same force just in the opposite direction at the same distance. So we still have a large force far away from the hinge, so we get a fast, in this case, closing. In contrast, compare A to B. We apply the force in B at the same position, same distance away from the hinge, but the force is smaller. So in this case, the door will open more slowly compared to A. In part C, we have the same size force as part A, but it's closer to the hinge. So in that case, the door will also open slowly. Now let's compare A to E. In part E, we have the same size force as part A. It's the same distance away from the hinge as part A, but the direction is different. And because the direction is the way it is in part E, the door will open more slowly than in part A. Finally, let's compare A to F. In situation F, we have the same size force as we did in part A. It is acting at the same distance from the hinge as part A, but we know that if we pull in this direction, the door will neither open nor close. So let's see if we can put all these ideas together. So this concept of torque depends on how hard we push, what force is applied. It depends on the direction of F in the sense that if we flip the direction of F, the rotation will be the opposite rotation. Sometimes it'll be clockwise, sometimes it'll be counterclockwise. It also depends on the direction of F in the sense that if I change the angle that F points, I can increase or decrease the quickness of the door opening. And it depends on how far away the force is from the point of rotation. So all of these ideas are encapsulated in this expression for torque. We use the Greek letter tau to represent torque, and it's equal to R times F times sine of theta. And here's a diagram showing those variables. I have an object, in this case a square, and I want to calculate torque about some point. One of the features of torque is you need to calculate torque about a point. And so in this case, I'm going to calculate torque about the lower left-hand corner. R is the distance from the point of rotation, or the point about which you're calculating torque, to where the force is acting. F, of course, is the force, and then theta is the angle between those two directions. So we say the torque created by this force about the lower left-hand corner is equal to R times F times the sine of theta. Now in some problems you can just calculate that. You can take the magnitude of F, the magnitude of R, take theta, and just calculate the value from that equation. But there are other problems where it will be easier to visualize this in a different way. So one of the ways we can look at this is we can take the sine theta and we can associate it with R. And we call that R perpendicular. Now visually, what does that mean? So same situation, I'm calculating torques about the lower left-hand corner. I have the force applied at the same spot. If I look at R sine theta, what that means is the idea of finding the perpendicular distance from this line of action to the point about which I'm calculating torques. So you can see that r sine theta is just this perpendicular distance. So this is what we call r perpendicular. It's the perpendicular distance, or the shortest distance, from this point to this line, the line of action, which is the line that goes through the force vector. A third way of visualizing it is to associate sine theta with the force, and that's what we call F perpendicular. In this case, what we want to do is we want to break the force vector up into components parallel and perpendicular to r. So this side we would call F parallel, this side we would call F perpendicular. And you can see that F parallel is adjacent to the angle theta, F perpendicular is opposite, and so I can say the torque created by the force F about the lower left-hand corner is equal to the perpendicular force times r. And what I mean by that is the force perpendicular to r. So now we have two conditions for equilibrium. We have sum of the forces equals 0, and we have sum of the torques equals 0. So let's take a look at example 9.1, but I want to do it in a slightly different way than what the book does. Example 9.1, two children are balanced on a seesaw of negligible mass. The first child has a mass of 26 kilograms and sits 1.6 meters away from the pivot point. The second child has a mass of 32 kilograms, and we're asked to find how far away from the pivot point she is, and also what is the pivot point doing, what force is it providing. So the way I'm going to do this is first draw a free body diagram. Put all the forces on it. And now we need to include distances as well. So there's my free body diagram. Now I have Newton's second law, and I have sum of the torques equals 0. So in the x direction,